Hello everyone. This is part 4 of the video presentation on module 4 data communication. So module 4 is basically dealing with the multiplexing, different multiplexing techniques. So in multiplexing, what is happening? The particular bandwidth that is available, which is a key resource in a communication system, is being shared among different sources and destinations. Okay, and how this sharing can be done, we already seen the basic analog multiplexing technique called the frequency division multiplexing, where the total bandwidth or the range of frequency is being divided for different sources, and accordingly the communication takes place. And you already seen the working principle of FDM. And now we move on to a variation of this FDM called the wavelength division multiplexing. See, it is as a name suggests, just like frequency division multiplexing, here we are supposed to divide the existing wavelength of the medium which we are having. And you know how this wavelength and the frequency are related to each other. So frequency means the number of times the cycles are repeating per unit time, right? Per time period. How many times the cycles are repeating, see how you can relate that with the time period. So if x unit of time is the time period, say x seconds is the time period, then frequency will be 1 by x hertz, right? If we are taking second and hertz as a standard unit. So how they are related like that? X second is a time period, means the time taken to complete a single cycle is x second. So that how many such cycles can be completed per unit second, and that will be 1 by time period. Okay, and similarly, you know what is wavelength? The wavelength is the distance traveled by the signal during one cycle. How long the signal is being traveled, that distance covered. So the normal equation of distance you can use, like speed is equal to distance by time. So distance will be speed into time. So what is the speed in which the signal is traveling into the time period, and this time period is again 1 by frequency. So that you can see that the wavelength and the frequency are inversely proportional to each other. Hope those derivations are clear for you. The wavelength and frequency are inversely proportional to each other, and a high frequency means a very small value for the wavelength. When frequency is coming in gigahertz range, wavelength will be in giga is what 10 raised to 9. Wavelength will be in nanometers. So like that. So the same concept only. So it's actually a variation of the, not variation, the frequency division multiplexing itself, but when it comes to multiplex optical signals, we are using the term wavelength division multiplexing. That's all. So wavelength division multiplexing is again an analog multiplexing technique, just like frequency division multiplexing, but here we are supposed to combine the optical signals, So wavelength division multiplexing is conceptually the same as frequency division multiplexing, except that the multiplexing and demultiplexing involve optical signals transmitted through fiber optic channels, and you know optical signals are transmitted through fiber optic channel, right? So how that multiplexing is happening in the within a fiber optic channel, how we are efficiently sharing the available capacity of the fiber optic channel, and that is what is called wavelength division multiplexing. Here also we are dividing the channel just like FDM only, but we are highlighting the term wavelength, okay, because when it comes to optical signals, the light waves which is coming under the visible spectrum, you can see that that color change, I mean different wavelength will be given different colors. So in that way you can differentiate the signals which are traveling through a common optical fiber. So that could be the reason they are separately dealing with the wavelength division multiplexing. We will see that the true potential of optical fiber is fully exploited when the multiple beams of light at a different frequency are transmitted on the same fiber, you know the capacity of a typical optical fiber. So it's providing very high capacity, especially when it comes to the backbone fiber optic cable, and that time to exploit the full capacity that is being provided to the user, there should be efficient mechanism for for sharing that existing capacity, the total capacity being available in the fiber optic cable. Such a sharing frequency sharing mechanism is what is wavelength division multiplexing. So this is a form of frequency division multiplexing itself, but is commonly called wavelength division multiplexing when it comes to multiplexing of optical signal. That's all, the same concept that we studied already, but only thing, the type of signal that is being handled by it is optical signal. That's all. In that context, the same FDM technique is called wavelength division multiplexing. So with the wavelength division multiplexing, the light streaming through the fiber consists of many colors or wavelength, each carrying a separate channel of data. So that is why we are highlighting the term like wavelength division. So when you are looking at the multiplexed signal, you feel like the total channel is being shared by different sources, and each source want to send some information through a particular wavelength or range of frequency, whatever it is, and that will be getting a different color with respect to the wavelength of the information. Okay, so all together you will see a collection of colors. The total optical fiber, if you observe its inside, you can see different set of colors are being traveled like that. So it is like if you are looking at the visible spectrum, we have this violet color for the shortest wavelength, and red color for the longest wavelength. Okay, so that is typically around, I think, 380 nanometer for violet and 700 nanometer wavelength for red color. So like that. So other colors are lying in between. So in that way you can so that is being highlighted here, that wavelength, when we combine different signals together, depending on the wavelength being used by that signal, it will be getting a particular color when it comes to optical signal, not for other signals in the electromagnetic spectrum. So this feature is particularly for optical signal, which are showing that different color for different wavelength. The same concept of frequency division multiplexing, when it comes to optical signals, we call it as wavelength division multiplexing. That's all. So in 1997, a landmark was reached when Bell Laboratories was able to demonstrate a wavelength division multiplexing with 100 beams, each carrying 10 gigabits per second, for a total data rate of 1 trillion bits per second. So what they tried to do, what this Bell Laboratories experimented is, they tried to combine 100 different input signals, say beams, and each of them is operating in 10 gigabits per second. So altogether 100 into 10 gigabits per second, it will be 1000 gigabits per second. That is nothing but trillion bits per second. Giga, the next unit is trillion. So like that, they demonstrated this concept, how optical signals can be multiplexed together, and for that experimentation we will be using prism, and that we will see how prism can be used to do this multiplexing and demultiplexing. Okay, so trillion bits per second is otherwise called terabit per second, or TBPS. Okay, giga units are like kilo, mega, giga, then tera. So commercial systems with even instead of that 100, currently we have 160 channels or beams of 10 gigabits per second are available now. So in that way we can view this wavelength division multiplexing. Now this figure shows that we are trying to combine three signals into a common channel, and at the receiver side we are trying to demultiplex them back to the particular receiver. So here we have three signals with three different bandwidth, lambda 1, lambda 2, lambda 3, and all of them are combined together with a common signal with the wavelength lambda 1 plus lambda 2 plus lambda 3, and it is traveling to the receiver side. It is demultiplexed back. And what is the technology behind it, we will see. wavelength division, the typical architecture of a WDM, and that will exactly like a FDM system. And we already seen the architecture of an FDM, how that multiplexing is done using a filter, how we are filtering at the receiver side, everything we already seen. So similar to that, the typical wavelength division multiplexing system has the same architecture as that of the other FDM system. A number of sources generate a laser beams at different wavelength. So here what is the difference from the normal FDM? Here we are dealing with the optical signals. So optical signals means basically laser beams, right? So they say the different sources generate different laser beams, of course with a different wavelength and accordingly the color coding. These are sent to the multiplexer, which consolidates all the sources of for transmission over a single fiber line. So multiplexer will be doing that many to one translation, and the multiplexed combined signal is traveled through the common fiber optic line, and on the way some 2000 meter around it is able to move the signal without any attenuation. But after some long distance, say 2000 meter plus, there will be possibility of signal attenuation. Now to tackle that, you can use optical amplifiers, right? So optical amplifiers, which are typically spaced tens of kilometers apart, simplify which are typically spaced tens of kilometers apart, amplify all the wavelength, I mean the combined multiplexed signal simultaneously, because it is traveling as a single unit right now. At the receiver side, finally the composite signal arrives at a multiplexer at the receiver side, where the component channels are separated and sent to the receiver at the destination point properly. The demultiplexing will be happening at the receiver side. Now we are achieving this with the help of a prism, and that is the basic technology within the wavelength division multiplexing. Although the wavelength division multiplexing technology is very complex, of course the basic idea is very simple. Only that basic idea is explained here. We want to combine multiple light sources into one single light at the multiplexer, and do the reverse at the just we want to combine different light signals, say with the different wavelength and accordingly different colors, and we want to combine them together, and at the receiver side we want to demultiplex back. So the combining and splitting of these light sources are easily handled by a typical prism. And now you can recall from the basics of physics that you already learned that a prism, the attractive property of a prism is that the prism can bend a beam of light based on the angle of incidence and the frequency. So the angle at which the signal is being incident on the prism and the frequency at which it is operating, both are affecting the bending of the signal when it is passing through a prism. So whenever a signal is incident on a prism, it will bend inside the prism and it will travel accordingly. And how much or what is the angle of bending, that depends on the frequency of the signal at which the signal is operating, and also the angle of incidence on the how it is what is the angle of incidence on the surface of the that will be measured with respect to a normal to the surface. Normally your signal is being incident on the prism with some angle with respect to the normal. Calculate that proportional to that angle of incidence and the frequency with which the signal is operating, it will be bending the signal to a different angle. Now using this technique, a multiplexer can be made to combine several input beams, and accordingly you have to make the input beams of light to incident on that particular prism at different angle, each containing a narrow band of frequency into one output beam of a wider band of frequency. So of course the output will be the combined one, so that should provide a wide band of frequency, but of course the sources will be sending the information with a very small narrow band of frequency. So from each source such narrow band frequencies are being combined together using a prism into a wide band frequency, and at the receiver side again using a prism, this wide band frequency containing the whole information will be demultiplexed back to narrow band information correctly into the respective receiver. So a demultiplexer can also be made to reverse a process. So typical diagram is shown here. This is the angle in which this particular information from this particular source or this particular signal with wavelength lambda 1 is being incident. You can measure the angle with respect to a normal to the prism. Similarly, this is another signal being incident on the prism with a different angle of incidence, of course a different frequency and or different free wavelength, whatever it is, right? So altogether the bending is happening like this, and you have to adjust this angle of incidence so that after making this bending all of them are getting combined together. Okay, so in that way we will be setting up the prism and the angle of incidence, and the signal will be traveling as a single unit over the fiber optic cable, and on the way if you want you can place the optical amplifiers, and after boosting and after traveling for a very long distance it will be reaching at the receiver, where the demultiplexer module of the receiver is again having a prism, and that will take this signal, and based on different frequency it will be bending the signal like this, and correctly it is delivered to the receiver. So that is this is just a diagrammatic view of what we explained, and some applications and typical improvements that are there for a wavelength division multiplexing concept. One application of a wavelength division multiplexing is of course the SONET, that is the synchronous optical network, in which multiple optical fiber lines are multiplexed and demultiplexed. So SONET is actually a backbone optical fiber network. Okay, so from the different that is typically traveling underneath sea, and from different individual machines using optical fiber cable, we will be connecting all the kind of branches into a common backbone, and this backbone is again optical fiber network with a very huge capacity, and that is what we call as a SONET backbone, synchronous optical network, something like that is the full form. And in that case definitely you can make use of wavelength division multiplexing to combine all the individual narrow band signals to this common SONET backbone. Okay, now as improvements you can think of something called a dense wavelength division multiplexing, which is a new method which can multiplex a very large number of channels by spacing channels very close to one another. So channel spacing means the distance between the central frequency of two adjacent channels. You know, the total frequency is being divided into different channels, and each channel or the smaller band of frequency carrying a particular information from a given source to a given destination is having a central frequency, and the adjacent band is also having another central frequency. So take the difference of between the central frequency of two adjacent channels within a common optical fiber network whose bandwidth is being shared among all the individuals, and that distance difference between the carrier frequency of central frequency of two adjacent channels is what we call as a channel spacing. And dense, of course, the word itself says that you are trying to combine. In the previous case we saw that 10 gigabits per second lines are being combined and experimented by Bell Laboratory, and currently we have 160 such a carrier that can be combined together. And as you are trying to combine more and more channels, that will be more and more dense. You know this term, right? Dense and sparse. Sparse means SPARSE, sparse. Just an opposite term to this dense. Dense means many are getting bundled together. Sparse means not many, very few are bundled together. For example, suppose you are combining 5 channels together, and into a common optical fiber cable, and using the same common optical fibers cable, suppose you are able to combine say 500 channels, and that 500 case will be dense where the 5 case will be sparse. Okay, so as you are making this more and more dense, the overall performance improvement will be high. In that case you can see that the channel spacing between the adjacent two channels is very very small. The channel spacing, they are very close to each other. That is why we can multiplex a large number of such channels together, making it dense wavelength division multiplexing. So what are the attractive points about this dense wavelength division multiplexing? It achieves even definitely greater efficiency because it is trying to combine more number of channels together. So in early system 200 gigahertz was allocated to each channel, the total width of each channel, but today most wavelength division multiplexing system use 50 gigahertz channel spacing, either the width of a particular channel or the distance between the center frequency of two adjacent channel. In both way you can think about the channel spacing. So right now we have a channel, we achieved channel spacing even up to 50 gigahertz. But in general, a spacing of 200 gigahertz or less is what we call as the dense. Even 50 definitely it is dense. So the threshold value is taken to be 200 gigahertz. So whenever you are trying to combine different signals into a common carrier, maybe optical carrier or somewhere else, hope you are clear about the concept of channel spacing. If the channel spacing is 200 or less than that, that is dense wavelength division multiplexing. If it is 200 or more, it is just normal wavelength division multiplexing. And you can think about another higher value, so that it will be sparse wavelength division multiplexing. But we are of interest on dense wavelength division multiplexing only because it is providing more efficient use of the underlying cable. So that's all. With this we will wind up discussion on wavelength division multiplexing. Hope you got an overview about it. Just like it is just as what we already seen, the detailed architecture, everything is seen for frequency division multiplexing. Everything is applicable here also, but instead of frequency, here we are highlighting the term wavelength, and we feel like the total wavelength of the channel is being shared. Okay, thank you. And in next part we will see the next major category of this multiplexing called the time division multiplexing. Thank you.